you've started flying, chances are you've probably done stalls already. Now if you haven't, don't worry, they're coming. It's going to happen in the next couple of flight lessons. Now the one thing that you probably have heard your instructor talk about is keeping the ball centered when you do the stalls. That's the one most important thing. And why do they talk about that? Well, here's what happens when you get into a stall without the ball being centered. You have a little bit of lift on one wing and almost no lift on the other wing. So the one wing that has lift ends up spinning you into a spin. And here's a video of what a spin looks like. Now this looks scary, and it should. Unless you're doing aerobatics training or you're doing spins with a qualified instructor, you shouldn't see this in your regular flying. This isn't really to scare you, it's to talk about how you recover from a spin if somehow you manage to get into one. Now first of all, to avoid getting into spins, if you're doing stalls, keep the ball centered. In your regular flying, you shouldn't be doing stalls in the first place unless you're training. But if you somehow manage to get yourself into a spin, you have to remember the acronym PARE, P-A-R-E. And what that stands for is power idle. So once you're spinning, bring the power to idle. The A stands for ailerons. Neutralize the ailerons if they're not neutral already. Next is R, which is rudder. Put opposite input on the rudder. In other words, if you're spinning to the left, put in right rudder. If you're spinning to the right, put in left rudder. And the last thing is elevators. Move the elevator forward to reduce the angle of attack and get the airplane flying again. Once you do get lift, once the airspeed starts increasing, you can slowly pull back and get back to level flight. Stalls and spins can be intimidating, and they should be to an extent, but the main point of practicing both of those is to know how to recover in case you get into one. If you've ever seen a boat, you know that boats generate wakes, and airplanes do too. We call that wake turbulence. So here's how it works. You have low pressure on the top, high pressure on the bottom. They come at the end, they meet up, and they move on happily ever after. And that's not the case on the wingtip. The high pressure on the bottom always tries to get to the top of the wing, and so it ends up creating a vortex. And that spins, if you look from the back of the airplane, it spins inward towards the fuselage. And that happens on both wings, both the left and the right side. Wake turbulence is generated when the airplane is producing lift. In other words, when it's flying. So it starts when the airplane takes off, and it doesn't stop until the airplane lands. So if you're taking off behind a heavy airplane, you need to make sure that you rotate before they do, and that you stay above their flight path, or you can turn to stay away from their wake turbulence. If you're landing behind a heavy airplane, you need to make sure that you land after they do, so you stay out of that area of wake turbulence. The most dangerous scenario is when an airplane is heavy, clean, and slow. And what that means is, well, heavy is self-explanatory. Clean meaning there's no flaps, so the angle of attack is high, which means there's a high difference in high and low pressure, and the slow part also means high angle of attack. So that's when your vortices, when your wingtip vortices will be the strongest, and that's when you should avoid them. To help with wake turbulence, you might have seen these on airplanes already. They're called winglets, little things that stick up above the wing, and that prevents the high pressure from the bottom from getting to the top of the wing, and so the wake turbulence gets reduced, and they're mostly found on commercial airliners. When an airplane gets close to the ground ends up interfering with the airflow patterns around the airplane. And so what happens is that air can't go down freely like it would in flight above the ground. And so it collects and it stays underneath the airplane, creating kind of like a cushion of air underneath the airplane. And so what that does is it generates a little bit of extra lift for the airplane. The airplane can get airborne at a slower airspeed than recommended. And then if you leave ground effect, you can stall the airplane just because you're slower than you normally would be. There are 4 left-turning tendencies when it comes to airplanes. Torque is an action-reaction force. The propeller, as viewed from the cockpits, spins to the right, and so the engine wants to rotate the airplane to the left. As the propeller spins, it creates a vortex of air that when it gets to the tail, it'll hit the tail on the left-hand side, and that'll rotate the airplane to the left. It's mostly noticeable when the propeller is spinning really fast, but you have relatively slow forward speed. So for example, when you're accelerating on takeoff, asymmetric loading or P factor happens because of the way the propeller is designed. When you're in a climb, the downgoing blade or the right hand side of the blade will be at a higher angle of attack than the upgoing blade or the left side. So what happens is you'll have more of an angle of attack, more thrust on the right hand side of the airplane than on the left, and the airplane will yaw to the left. So your instructor will probably keep telling you to keep adding right rudder when you're climbing, because you'll see that your ball or your inclinometer will be off to the side just a little bit. Another left turning tendency is gyroscopic precession. If you've ever seen one of these things, this is a gyroscope. Basically it's a wheel that you can spin really fast, and then it has some pretty cool properties associated with it. So we'll give this a spin and I'll try to show you if it works, what happens to the propeller. Basically when I try to tilt this forward, it doesn't want to go forward. You can see how I push it forward, but it kind of goes over here. And that's because the force that you apply acts 90 degrees forward of the rotation. So it's kind of hard to actually tilt this thing straight back and forth because of that gyroscopic force. You can kind of see how it just tries to go somewhere you don't want it to go. So that's a bad example, but gyroscopic precession is when you apply a force but it's felt 90 degrees forward of its rotation. And this applies really well to tailwheel airplanes, because when you're taking off in a tailwheel airplane, you have to bring the tail up to get the airplane off the ground. So you bring the tail up, you apply a force over here, but it's actually felt 90 degrees forward, and the airplane ends up yawing to the left. Those are four forces: gyroscopic precession, P factor or asymmetric loading, slipstream, and then torque. So those four are your left turning tendencies. Adverse yaw is something that happens all the time when you're turning, and it's why you need a rudder in the turn. When you turn the ailerons, let's say to the right aileron will go up and the left aileron will go down. And so what happens is the aileron that goes down will end up creating lift, but it will also create drag. So the left wing will go up, but it will also go back. So you'll have the airplane banking, but also yawing in the opposite direction of the turn, and that's why we call it adverse yaw. And so when you're turning, you'll have to make sure that you apply the rudder in the direction that you're going. So if you're banking to the right, you'll have to add a little bit of right rudder when you're making that turn. Manufacturers do try to overcome these left turning tendencies and adverse yaw by doing things like changing the aileron deflection so that the up and down aileron don't go up and down the same distance, or they'll offset the vertical stabilizer, or maybe offset the engine off center just a little bit. But you as a pilot are the primary person keeping the airplane coordinated and flying at all times. So keep the ball in the middle and everything will go smoothly for the most part. To end this video, I've got a little question for you. So if you wanted more lift, you could make a bigger airplane wing. Can the same be said about a propeller? Why not raise an airplane a few feet off the ground and, let's say, double the size of a propeller? What's stopping manufacturers from doing that? Tell me your answer in the comments below. And in the description box, as always, there will be reading material to cover the same stuff I covered in more detail. That's usually the Pilot Handbook of Aeronautical Knowledge. So go ahead and check that out. And after reading that, if you still have questions, feel free to comment down below and I'll try to answer them. And as always, have fun, fly safe, and always keep learning. See you next time.